So as of now in chapter 5 we have discussed the Newton's first, second and third law, the free body diagram, contact forces, forces in one dimension and two dimension. Now we'll discuss the weight of an object. Okay. Now whenever you ask a person that what's your weight, he generally says that my weight is 75 kgs or 80 kgs, something like that. Is 75 kgs a weight? No. 75 kg is the mass of the person. So what is the weight? The weight of any object on Earth's surface is simply the gravitational force exerted on it by the Earth. Now let us discuss the relationship between the mass and weight. Now suppose an object having mass is in free fall. Now the only force acting on it is the gravity force, its weight. Now let's apply the Newton's second law of motion in the vertical direction, and we have taken the upward direction to be positive. So we can write that sigma Fy is mass times Ay. Now Ay we have minus g, and the net forces is also in the downward direction, so we can write that minus W is equals to minus mg. From here we'll get the weight of the object of mass m is W equals to m times g. Therefore from here the weight of an object of mass m is equals to mg. Now concluding everything, we can write that weight is a force which is equals to mass times g, and it's a vector quantity, and the unit we have Newton, and the direction of weight force is same as the direction of g, that is acceleration due to gravity. Now suppose there's a person whose mass is 70 kg on Earth. Now what would be its weight? So weight on Earth, this will be m times g. Mass we have 70 kgs, and the value of g we have 9.81 meter per second squared. From here the weight comes out to be as 696.5 Newton. Now will the weight be same on Moon? No. Although the mass will remain same on the Moon, as the amount of matter in it remains the same regardless the location, but the weight will going to change. What would be the weight? So weight of the same person on the Moon, this would be equals to m times g. This g we have to take g for the Moon. The g for Moon is 1/6 of g on Earth. So the weight would be m times mass we have 70 kgs, and the value of g on Moon we have approximately 1.62 meter per second squared. So from here the weight is 115.02 Newton. The same person weighs this much on Earth, and the same person weighs this much on the Moon. Now let's discuss an example. Now we have a person whose mass is 97 kgs and it slides down 3 meter to the ground. Now suppose that the fireman starts from rest, so its initial speed we can take it to be 0, and it moves with constant acceleration, okay, then reaches the ground in 1.2 seconds. So time is 1.2 seconds. Now we need to find the upward force F exerted by the pole on the fireman. Okay, so first of all what I'm going to do is I'm going to make a free body diagram, and I've taken this direction to be positive y. So this is the point mass. Now the weight force would be acting in the downward direction, W, and this force F by the pole on the fireman is F. It is acting in the upward direction. Now you may think that how pole exerts the force on fireman. The reason is, as the person slides down, he exerts the force on the pole, and by the Newton's third law, the pole also exerts an upward force of equal magnitude on the fireman, and these forces are due to friction that we'll explore in the next chapter. So that is why this force F is here. Now we need to find this force F. Now for that we're going to use the Newton's second law of motion, which says that net force acting on an object is m times Ay. We can equate these, but we don't have the value of ay, the acceleration. So we can find it by using the kinematic equations. So if you use this equation, y is equals to y naught plus v naught y times t plus 1 over 2 ay t square. Now this is the coordinate system where I have taken this to be the 0, and here the y values are increasing. Now when the fireman reaches on the ground, the final position becomes 0. So this is 0. Initial position we have 3 meter. This is 3. Plus initial velocity is 0. So this terms goes to 0. Then we have 1 over 2 ay. Ay we need to find. Now time taken by the person to reach on the ground is 1.2 seconds. So this is 1.2 seconds and its whole square. From here we can easily find ay, and this value comes out to be as negative 4.2 meter per second squared. Why this is negative? Because the acceleration is in downward direction. Okay, now we can apply the Newton's second law of motion. So sigma Fy is m times ay. Now net forces acting on the object, sigma Fy, this will be equals to, now upward direction we have taken positive, so this is plus F, downward is negative, so minus W. This will be the net force. So we can equate sigma Fy to be m times ay. So F minus W is equals to m times ay, right? From here F will be equals to W plus m times ay. Now what is weight? Weight is m times g, that we studied just now. W is m times t. Now from here the force F, this would be equals to m, we can take common, g plus ay. Now the mass for the person is given to be this is 97 kg. This is 97 kgs. G is 9.81. Ay we have minus 4.2, so minus 4.2. So on solving we'll get the force to be equals to 540 Newton. Now if you want to write the force in vector form, so this force F, this would be 540 Newton unit vector y cap. Now we're going to discuss the term apparent weight. So we all have experienced when an elevator is accelerating upwards, we feel heavier, and when it is accelerating downwards, we feel lighter. So the motion of an elevator can give rise to an apparent weight that differs from our true weight. But why? Well, in this case, the sensation of weight is due to the force exerted by the floor of the elevator on your feet. And if this force is greater than your weight, mg, you will feel heavy. On the other hand, if this force is less than mg, you will feel light. Now let us understand this by using the Newton's second law of motion. So suppose you are in an elevator that is moving upwards with an acceleration a. Now let us try to draw the free body diagram of the person. So this is the point mass that we consider. Now the weight of the person is vertically downward. This is W. Now the upward force exerted on your feet by the floor is WA. Now this WA is the apparent weight, or the force that pushes upwards on your feet and gives you the sensation of your weight pushing down the floor. Now we can apply the Newton's second law to find the value for this WA. So the net forces in the vertical direction, this direction we are taking to be positive. So sigma F y, this would be WA minus W. And from the Newton's second law we can write that sigma Fy, this is equals to m times ay. Now ay we have equals to a. From here this sigma Fy we have WA minus W is equals to m times a. Now from here WA, this will be equals to W plus MA. Now what is weight? Weight is m times g. So we can put it here. So WA, this will be equals to mg plus MA, which can also be written as, we can take m common from here, so g plus a. So here we notice that your apparent weight WA is greater than your actual weight W. Hence you will feel heavier when this elevator is accelerating upwards. Now think what would happen if the same elevator is accelerating downward. Then in this case, Ay would become minus G. So this equation would become A equals to M times G minus A. So this time your apparent weight is less than W. So this time you'll feel lighter. So this is the concept for the apparent weight. Now in the next video, we'll see a couple of more questions on this topic and then we'll start the normal forces.